A furious typhoon slams into Hong Kong, whipping Victoria Harbour into a wall of treacherous, churning ocean water. Hundreds of thousands of terrified workers crowd the docks, desperate to return home as ferries rock violently against the piers. When the storms strike, these surface boats instantly paralyze, completely cutting the island off from the mainland. City leaders realized that if Hong Kong were to survive its booming future, it needed a permanent cross-harbor connection. Their daring vision was to run an express train line directly through the heart of the raging sea. Yet the sea floor was a nightmare of soft mud, volatile sediment, and violent underwater currents. Conventional wisdom warned that building a stable structure down in this underwater abyss was practically impossible. One single crack under the immense crush of water would instantly drown hundreds of trapped passengers. The water pressure on the harbor floor is unrelenting, pushing against every square inch with staggering force. That weight is equivalent to balancing 3 heavy SUV cars on a surface no bigger than a postage stamp. To defeat this liquid barrier, engineers had to throw standard construction manuals completely out the window. They attempted a radical, terrifying method that no city had ever attempted at this massive scale. Victoria Harbour is one of the busiest maritime shipping lanes in the world, filled with giant cargo ships. Standard bridge designs were rejected immediately because massive support towers would choke vessel navigation and destroy harbor traffic. A bridge would also leave trains exposed to typhoon winds strong enough to blow freight containers off decks. So, engineers turned their eyes downward, contemplating a conventional tunnel dug deep underneath the seabed soil. They brought in giant drill machines, hoping to bore through the rock far beneath the ocean floor. However, subterranean tests revealed soft, liquid mud and unstable, decomposed granite underneath the seabed surface. Digging through this structural soup meant the ocean roof above could collapse into the drilling shield without warning. A single drill head hitting a soft pocket would flood the tunnel with thousands of gallons of seawater per second. Workers faced the constant threat of drowning in absolute darkness hundreds of feet beneath the surface. Every standard idea had failed, leaving the growing city on the brink of a severe transportation collapse.
The logistics involved in managing this many vessels require precision engineering. As you can see behind me, operations are non-stop.
The breakthrough idea was astounding in its simplicity. Build the tunnel in pieces on dry land first. They would construct hollow concrete blocks, float them into position, and sink them directly onto the sea floor. This concept is called an immersed tube tunnel, turning heavy marine engineering into a game of underwater building blocks. Instead of battling nature underwater, workers could build perfect concrete segments inside the safe, controlled environment of a dry dock. Each massive concrete block measured over 300 feet long, stretching longer than a professional football pitch. When fully constructed, a single hollow block weighed over 11,000 metric tons. That is heavier than 80 blue whales combined floating on top of the water. To make these giant concrete monsters float, engineers temporarily sealed both ends with massive steel walls called bulkheads. Trapping air inside turned these giant concrete blocks into hollow, floating barges ready for transport. Tugboats pulled the massive structures out into open harbor waters like floating skyscrapers laid on their sides. An engineer studies the navigation readings, his expression tightening as unpredictable harbor currents threatened to push the block off course. The margin for error was non-existent. Dropping one slightly off target would ruin the entire project permanently. Inside the dry dock, teams worked round the clock, weaving giant concrete skeletons strengthened with heavy steel bars. Special concrete mixtures were tested rigorously to guarantee resistance against chemical erosion from salty seawater. A single microscopic crack in the concrete matrix would allow salt water to rust internal steel supports over time. Simultaneously, giant dredging ships worked out in the harbor, carving a deep trench into the muddy seabed floor. Dredging buckets scooped up thousands of tons of soft mud, clearing a stable channel for the incoming tunnel segments. The total earth moved could fill a major football stadium clear to the roof twice over. Once the trench was carved, workers prepared a flat bed made of crushed foundation stones at the trench bottom. Deep-sea divers descended into murky waters, working in near-total darkness to inspect the gravel bed leveling process.
The water was pitch black, a diver's log noted, highlighting the reliance on touch rather than sight down there. Strong underwater currents repeatedly threatened to sweep the divers off their feet into the dark abyss. To keep the trench floor level, specialized underwater surveying tools mapped the gravel using sound waves. The foundation had to be precise down to the width of a human finger over thousands of feet. With the trench prepared, the stage was set for the most dangerous phase of construction ever attempted in Hong Kong. Right now, specialized barge rigs position themselves directly above the deep underwater trench in Victoria Harbour. Engineers pump thousands of gallons of water into internal ballast tanks inside the sealed concrete structure. The extra water weight slowly overcomes the natural floating force, forcing the massive concrete block to submerge gently. Tension cables creak on the surface cranes as 11,000 tons of concrete slowly descend beneath the surface waves. Subsurface currents hit the dropping block, pushing it sideways toward the rugged rock walls of the open trench. Operator monitors controlling winches, his face taut with extreme focus as he corrects the lateral drift. If two adjacent concrete blocks collide during descent, their delicate sealing edges will shatter instantly, beyond repair. The giant block hangs just inches above the ocean floor, swaying gently in the dark current.
As you can see, the winches behind me are straining under the pressure. This is the most critical phase of the operation, and the stakes could not be higher.
Engineers use hydraulic positioning jacks to guide the massive concrete block into its exact position against the previous segment. They line up the giant blocks with millimeter accuracy, using laser alignment systems shooting through underwater sight ports. The connection must be virtually perfect. An alignment error of half an inch ruins the entire subway track line. A heavy steel pin on one segment aligns with a receiving socket on the adjacent segment, locking them together. With the structure aligned, giant machine-powered jacks pull the new segment tight against the existing underwater tunnel section. As the two massive faces meet, a flexible rubber gasket ring around the rim compresses under immense pressure. Trapped water between the temporary end walls is pumped out, creating a vacuum inside the small joining chamber. The outer ocean pressure now slams against the far end of the block with astounding physical force. This natural ocean weight acts like a giant hydraulic press, squeezing the rubber seal flat and watertight. Engineers step inside the dark, dry connection chamber, listening intently for the faintest sound of leaking water. Silence reigns. The ocean is held back completely by the sheer mechanical force of its own crushing weight. To understand how this tunnel survives beneath the sea, imagine squeezing a soft rubber ring between two heavy mugs. If you push hard enough, no liquid inside can escape through the tight rubber barrier you created between them. In Hong Kong's underwater tunnel, the sea itself provides that crushing, pushing force, securing its own outer containment. Once locked, workers inside slice open the temporary steel walls, opening a continuous dry highway deep beneath the waves. Heavy rocks and gravel are dumped over the submerged tunnel to bury it completely beneath the natural seabed. This heavy soil armor protects the concrete segments from runaway ship anchors dragging across the harbor floor. Inside the tunnel, flexible movement joints connect the rigid concrete blocks together like a long, bendable spine. If an earthquake shakes the sea floor, these flexible rubber joints absorb the movement without cracking the concrete walls.
The design allows the entire structure to flex safely during ground tremors, preventing sudden structural snapping under pressure. Ventilation shafts rising above the water surface continuously pump fresh air down into the deep subterranean train paths. High-capacity emergency water pumps stand ready along the floor track to remove any ambient condensation automatically and instantly. What was once an impossible underwater boundary turned into a seamless, high-speed rail corridor beneath the harbor. Just months after completion, a Category 10 super typhoon violently strikes the Hong Kong coast without mercy. Monster waves crash over harbor retaining walls, destroying surface shipping docks and flooding major coastal roadways instantly. Surface travel halts completely across the territory as screaming winds reach over 140 miles per hour. Deep beneath the ocean surface, the newly installed underwater train tunnel faces its ultimate real-world survival challenge. Enormous wave energy surges above, creating massive dynamic pressure changes directly over the buried concrete tubes. Sensors installed along the interior concrete lining begin registering subtle structural shifts as forces ripple through the earth. An operator inside the central control room watches the monitor bank anxiously, checking for sudden pressure drops or warnings. Out in the harbor, shifting seafloor sediments move around the outer rock armor under the force of currents. Yet inside the sunken concrete tube, the structural movement joints flex precisely as designed by the engineering team. The compressed rubber seals hold their ground, denying entry to millions of gallons of heavy ocean water above. High-speed trains continue gliding smoothly through the underground darkness, completely unaffected by the apocalyptic storm outside.
As you can see, the future of transit is here. We are thrilled to launch the Underwater Express, arriving right on schedule.
Commuters travel safely across the sea in minutes, entirely oblivious to the natural destruction raging overhead. The daring engineering project passed its trial by fire, proving that human ingenuity could indeed conquer the sea. Hong Kong had successfully constructed an indestructible lifeline right through the treacherous heart of its famous harbor. Today, millions of passengers cross Victoria Harbour every week through this incredible, hidden underwater railway line. What was once considered an impossible engineering gamble set a bold new standard for coastal infrastructure worldwide. Engineers proved that by working with the physics of the ocean rather than fighting it, even extreme nature can be mastered. Deep beneath the dark harbor currents, Hong Kong's underwater train continues running quietly, defying the ocean every single day.